Hello and welcome back. In this video, we're covering section 7.6. So we're continuing our exploration into some additional trigonometric identities and formulas, and this is on double angle and half angle formulas. So last time we were looking at angle addition and subtraction, so like the sine of the sum of two angles or the subtraction of two angles. We saw that for sine, cosine, and tangent. So double angle means like twice, like 2 theta, twice of an angle, or half angle, we can imagine theta divided by 2. So this will further expand our ability to evaluate some trig expressions that aren't necessarily unit circle angles, but maybe twice one or half of one. So let's see how these are defined. So we're going to start with the double angle formulas, and they throw a bunch of them at us here. So let's see where these are coming from. We'll start with the sine of 2 theta. They say this is ultimately equal to 2 sine theta cosine theta. Well, a double angle, sine of 2 theta, we can reference back to angle addition because we can express the sine of 2 theta as the sine of theta plus theta. And we saw last time angle addition for the sine of a plus b, or alpha plus beta. In this case, it's theta plus theta. It's the sine of the first angle times the cosine of the second angle plus the cosine of the first angle times the sine of the second angle. And here the first and second angles just happen to be the same angle. So we get two of the same terms. The second one is flipped around, but we can exchange the order of that multiplication, make it sine times cosine. So we can see that this will give us 2 sine theta cosine theta. That one's simple enough. Let's do the same for the cosine of 2 theta. Let's express it as angle addition. And notice cosine 2 theta has three different descriptions here. So let's see how we can get each of these. So cosine 2 theta we can express as the cosine of theta plus theta, just like we did for the sine. And angle addition for the cosine is the cosine of the first angle times cosine of the second angle minus minus sine of the first angle times sine of the second angle. So notice this will give us cosine squared minus sine squared. So that's our first identity there. So cosine squared minus sine squared we can write is cosine of 2 theta, and vice versa. But notice there's these other two descriptions as well. So what we can do is take the fact that we can express cosine squared or sine squared in terms of the cosine or sine. But let me show you what I mean by that. So this is coming from the Pythagorean identity, sine squared plus cosine squared equals 1. Well, if I subtract sine squared over, I can say cosine squared equals 1 minus sine squared. Or if I subtracted the cosine squared over, I can say sine squared equals 1 minus cosine squared. So these are useful. We can express the cosine in terms of the sine, or the sine in terms of the cosine if they're squared. Meaning, in this identity we just created, cosine squared minus sine squared, I can replace the cosine squared with 1 minus sine squared. And then we have minus another sine squared. So notice that will give us our 1 minus 2 sine squared. Or instead, I can keep the cosine squared there and replace the sine squared with 1 minus cosine squared. So notice this will be cosine squared minus 1 plus cosine squared, because the double negatives will make it positive. So we'll have 2 cosine squareds minus 1, and that's our third version. 2 cosine squared minus 1. So cosine of 2 theta is pretty versatile. You can express it in these 3 different ways. So we get these 3 identities for cosine of 2 theta. Sine of 2 theta just gets that one expression. So with these in mind, let's go through a few examples. So this says if sine is 3/5, sine of theta is 3 over 5, and theta is between pi over 2 and pi, so in the second quadrant, find sine of 2 theta and cosine of 2 theta. What's worth finding out, they give us the sine of theta. Let's find out what the cosine is based off of this description. We're in the second quadrant, so I can imagine some triangle. Sine is opposite over hypotenuse. And this looks like a 3, 4, 5 triangle, so this should be a minus 4. This distance should be negative since we're in the second quadrant. So that means the cosine should be negative 4 over 5, adjacent over hypotenuse. And we can get this via the Pythagorean identity too, if we wanted to just use sine squared plus cosine squared equals 1. We can plug 3/5 in for sine and then solve for the cosine, and you'll get plus or minus 4/5, and then you would use the quadrant information to decide that the cosine should be negative, since we're in quadrant 2. So now we know what sine and cosine of theta is, so pretty much just need to plug into our formulas. Part A asks for the sine of 2 theta. We said earlier that is 2 sine of theta cosine of theta. So that would be 2 times 3/5, that's the sine of theta, times negative 4/5, that is the cosine. So let's say that will be over 1. So 2 times 3 times negative 4, that's 2 times negative 12, so negative 24, and we have 2 5s in those denominators, so over 25. So a lot of times with these kind of questions, they'll give you some limited information, maybe just the sine or just the cosine, and usually the first step is to find your missing trig expression, because all of these involve sine of theta and cosine of theta. We saw a similar thing with the angle addition questions as well. So let's do part B. This wants the cosine of 2 theta. And we just saw we have 3 different definitions. We can use any one that we want to. Let's just use that first definition of it being cosine squared minus sine squared, since we know both sine and cosine. So this would be negative 4/5 squared minus 3/5 squared. So that will become positive 16 over 25 minus 9 over 25. 16 minus 9 is positive 7. So 7 over 25. So just need to find our right formula, maybe find our missing trig value. In this case, we wanted to find the cosine, then plug everything in and simplify. All right, just like last time, we can use these identities in order to establish additional identities. So let's start. First, it has us find out the formula for the tangent of 2 theta. So we can do the sine of 2 theta over cosine of 2 theta if we want to, but we can also see this as the tangent of theta plus theta. So last time, maybe I'll write it out here first. The tangent of the sum of 2 angles, I'll say alpha plus beta, was the tangent of the first angle plus the tangent of the second angle over 1 minus tangent of the first angle times the tangent of the second angle. So let's just plug in theta for both of these angles. So we would get tangent theta plus tangent theta over 1 minus tangent theta times tangent theta. We can combine some like terms here. We have 2 tangent thetas on top, so that can become 2 tangent of theta over 1 minus, and that will become tangent squared, because we have 2 tangent of thetas multiplied together. So this is actually the double angle formula for the tangent. If you have the angle addition ones already, you can use them to rederive your double angle formulas if you need to. Part B asks us to develop a formula for the sine of 3 theta in terms of sine and cosine. Well, we can express the sine of 3 theta as the sine of 2 theta plus theta. So let's first apply the angle addition formula, and then we'll work on that double angle. So we said earlier, sine of sum of 2 angles is the sine of the first angle times the cosine of the second angle plus the cosine of the first angle times the sine of the second angle. And then now we have formulas for sine of 2 theta and cosine of 2 theta. So let's substitute those in. So I'm going to replace that sine of 2 theta with how we defined it earlier as 2 sine of theta cosine of theta. And then we also have times this other cosine. Then we have the cosine of 2 theta. So we can use whichever one we want to. Um, let's try to express this all in terms of just the sine of theta, ultimately. So I'm going to use the formula for the cosine of 2 theta as 1 minus 2 sine squared times the sine. All right, let's keep simplifying. So the first term, notice we have 2 cosines multiplied. That's 2 sine theta times cosine squared. And then let's distribute this sign to both terms here. So this will become plus sine of theta minus 2 sine cubed and then we still have this cosine squared, but let's express it as 1 minus sine squared theta. We saw we can do that too. Just so that everything is in terms of the sine. And then we can distribute that 2 sine theta through to both terms. So this becomes 2 sine of theta minus 2 sine cubed plus 1 sine of theta minus 2 sine cubed. Then we can combine all of our like terms. It looks like we have 2 sine theta plus sine theta, so that will become 3 sine of theta. Then minus 2 sine of theta minus 2 sine cubed minus another 2 sine cubed. So those will combine to become minus 4 sine cubed theta. So we can stop there. We can't combine any additional terms. So we've actually produced another identity now for the sine of 3 theta. This isn't one that you need to memorize or anything, kind of just doing this as an exercise of applying these all these different identities. And we could have tried to maybe express this in terms of the cosine or have some mixtures of sine and cosines. So this just goes to show that there's many different identities that we can apply and we can express things in different ways as well. So, but again, for this one, it's really about just applying our double angle addition identities all together in order to create an expression. All right, so we have now the tangent of 2 theta added to our collection of double angle formulas. And we derived that earlier. The tangent of 2 theta is 2 tangent of theta over 1 minus tangent squared. But we also have what's called half angle identities. And we can start to derive them. They give us one here, and let's see where it's coming from. Let's start with the cosine of 2 theta. And we'll use the definition in terms of sine squared. We said earlier this was 1 minus 2 sine squared of theta. So let's solve this for the sine squared. So I can add the 2 sine squared over to the other side. And let's go ahead and already subtract the cosine of 2 theta over to the right side. So this can be re-expressed as 2 sine squared theta equals 1 minus the cosine of 2 theta. And then we can divide both sides by 2. So sine squared equals 1 minus cosine of 2 theta divided by 2. Eventually, eventually you'll see a form of this identity where they take the square root of both sides and involve a plus or minus. And then we'll look at expressing these angles a little bit differently. But the main thing to notice now is this angle is half of this angle. So we will re-express that in a little bit. We can do a similar thing too for the cosine. And the starting point is the same in terms of starting with the cosine of 2 theta. But let's use the definition involving cosine squared. We said this was equal to 2 cosine squared theta minus 1. So let's solve this one for cosine squared. So let's just flip this around to start with. We can say 2 cosine squared theta minus 1 equals cosine of 2 theta. I can add 1 to both sides. And then divide by 2. So cosine squared of theta can equal cosine of 2 theta plus 1 over 2. And then similarly here, we'll see in the full half angle identity, they'll take the square root of both sides and then re-express these angles. But again, notice this angle is half of the angle on the right side. And then let's do the same for the tangent as well. Here we can use what we just built. If we see the tangent squared as sine squared over cosine squared, so we said earlier sine squared can be replaced with 1 minus cosine 2 theta over 2. So let's plug that in. And then in the denominator, cosine squared, we just said we can write as, we can change the order of that addition. We can say 1 plus cosine 2 theta over 2. So if you do this division of two fractions, the second fraction will flip and multiply, and you'll see that those 2's will cancel, because this is really times 2 over 1 plus cosine of 2 theta. So the 2's cancel, and we end up with the 1 plus cosine 2 theta in the denominator. So this can be written as 1 minus cosine of 2 theta over 1 plus the cosine of 2 theta. So we get our identity that's shown here. And similarly here, we'll end up taking the square root of both sides. So there's nothing to memorize with these three. We're really just kind of setting ourselves up to ultimately get our full half angle identities. So let's hang on to these for now. So let's see how we can use these with a couple examples here. So example 3 says to write an equivalent expression for the cosine of 4 theta that does not involve any powers of sine or cosine greater than 1. Well, we just saw that we have this expression for the cosine squared. And let me write that here just so we can reference. We know that the cosine squared of theta can be expressed as the cosine of 2 theta plus 1 over 2. You can view this as like a power reduction formula. I think I've heard it described in that context as well. Because we're reducing the power from being squared to being in the first power. So let's try to express this in terms of cosine squared. It's cosine to the 4th power, so we can rewrite this as cosine squared of theta itself squared. So let's use this formula to replace cosine squared. We're trying to reduce the power here. So we still have this big outer square happening, but inside we can replace it with cosine of 2 theta plus 1 over 2. And this is being squared, meaning the numerator will be multiplied by itself and the denominator will also be multiplied by itself. So we have like 2 factors of cosine of 2 theta plus 1. So let's multiply that out. Let's expand it out, because we still need to evaluate this outer square. So the first term, we'll get cosine of 2 theta times cosine of 2 theta. So that should be cosine squared of 2 theta. Then plus cosine of 2 theta, and then plus another cosine of 2 theta. So I'm just imagining we're foiling this. So we'll get 2 of those. And then the last terms will be 1 times 1. And then our denominator gets squared as well, so this should be over 4. But we're still trying to express this in terms of cosine to the first power. So we need to effectively do the same thing with that cosine squared. So we'll apply this formula again. Let's first split everything up into separate fractions so we can kind of treat this piece by piece. So what I mean by that is I can write this as cosine squared of 2 theta over 4. Or we can put the 1/4 out in front. 1/4 cosine squared 2 theta. Plus our second term would be 2 cosine 2 theta over 4. And the 2 over 4 will reduce to 1/2. So I can write that as 1 over 2 cosine of 2 theta. And then my last term is 1/4. Alright, now let's apply the same identity, this one that we used here, to this cosine squared of 2 theta. So this will become 1 over 4 times, now notice here, if we're inputting 2 theta inside, then this should show up as twice that angle, or in our case that would become 4 theta. So this will be cosine of 4 theta plus 1 over 2. Then we still have plus 1/2 cosine of 2 theta plus 1 over 4. Let's make a little more room here. Okay, so how will this simplify further? Well, we can do a similar thing where we split up this fraction into 2 fractions. So I can make this 1 over 4 times, write that as 1/2 cosine 4 theta plus 1/2 plus everything else here. Let's distribute that 1 over 4 through. So this will become 1 over 8 cosine 4 theta plus 1 over 8 plus 1/2 cosine 2 theta plus 1/4. And then we're almost there. We just need to combine this 1 over 8 and 1 over 4. 1/4 plus 1/8. That's like 2/8 plus 1/8, or 3 over 8. So this will reduce to 1 over 8 cosine of 4 theta plus 1/2 cosine of 2 theta plus 3 over 8. Now, this is kind of a weird problem in the context of what we've been looking at in this course of pre-calculus. Because you may ask, like, what is the utility of taking something kind of nice and very simple, like the cosine to the 4th power, and expressing it as something admittingly kind of uh, like pretty complicated, some complicated expression like this. And this, unfortunately, is another example of us learning a process that will become extremely useful in the context of calculus and in the context of taking integrals and more higher level operations. There'll be a time where it'll be of interest to try to re-express things in terms of cosine to the 1st power, even if we have more messy angles in these fractions, due to being able to apply certain integration techniques to them that'll be simpler than having to try to figure out this power. So it might be useful to split it up in terms of a bunch of maybe easier pieces to evaluate. So I know that's kind of less satisfying at this point, but this is a skill that will come into use at a later time. But the giveaway in terms of the instructions here is to write an equivalent expression that does not involve any powers of sine or cosine greater than 1. So we're trying to reduce the power. So that's where these like intermediary formulas become useful here. All right, let's look at example 4. It says to solve the equation sine of theta times cosine of theta equals -1/2. And they tell us that theta is in between 0 and 2 pi. So what can we do? Well, I see sine times cosine, and that makes me think of the identity, the double angle identity for sine. Sine of 2 theta is 2 sine cosine. So let's multiply that 2 over to the other side and see if that will be useful for us. This becomes 2 sine theta cosine theta equals -1. And 2 sine cosine theta we can rewrite as sine of 2 theta. So let's do that. So sine of 2 theta equals -1. Now let's solve this as a trig equation. Now we have just a single sine function. So we can use a substitution method, which I showed in a previous video, or we can just think in general, where's the sine of something equal to -1? And let's just take the 2 theta along with us. Well, sine of overall 2 theta, the sine of anything is equal to -1 at 3 pi over 2. That's the coordinate point 0, -1. But then also all coterminal angles to that point. So we can say 2 theta must equal 3 pi over 2, but then the general solution is plus, we can say 2k pi, where k is any integer. And this is the general solution that captures all possible coterminal angles to 3 pi over 2. Now we just need to solve for theta, so let's divide everything by 2. So theta will equal 3 pi over 4, and this term also gets divided by 2, plus k pi, so multiples of pi, again where k is any integer. So let's list all solutions between 0 and 2 pi. So theta must equal our starting angle of 3 pi over 4. And then if we add another pi to that, if we add 4 pi over 4, that will give us 7 pi over 4. So just short of 2 pi, which would be 8 pi over 4. So we'll have to stop there. If we add another pi, we'll be outside of our restricted interval there. So we can use these identities in the middle of solving a trigonometric equation as well. In order to simplify things to a form where we can get some solution out of it. Alright, our last section is getting these full half angle formulas. And notice, so we're starting from these previous statements that we got. You can call this like a power reduction formula. We said sine squared. Notice they've changed the way that they've expressed the angles. That's kind of what I was hinting at earlier. So let's just take a look at that just to make sure that that makes sense before we move forward. So earlier we said sine squared of theta equals 1 minus cosine of 2 theta over 2. So one way we can look at this is just dividing each of these angles by 2. So if this is true, then we can say the sine squared of theta over 2, so dividing that angle by 2 equals 1 minus cosine of just theta, because 2 theta divided by 2 will just give us theta over 2. So that's what I meant by like re-expressing these angles, and we still have that situation where this angle is half of this angle. And then we can ultimately take the square root of both sides. So I could say the sine of theta over 2 equals plus or minus the square root of the right-hand side. 1 minus cosine theta over 2. So this is what we're calling a half angle formula. So just to explain where these are coming from. So we can see the same statement here. We have a similar one for the cosine that we saw earlier, and also for the tangent, just in terms of expressing it as a half angle. And then if you take the square root of both sides for each of these, we get our, what they're calling half angle formulas. So the plus or minus we'll have to determine depending on which quadrant we're in. But we have one for the sine, plus or minus root 1 minus cosine of our angle divided by 2. They're using alpha here, but we can just as well use theta. Then for the cosine half angle, plus or minus square root of 1 plus the cosine of alpha over 2. And for the tangent of alpha over 2 half angle, plus or minus the square root of 1 minus cosine alpha over 1 plus cosine alpha. And I make that note here, where the plus or minus is determined by the quadrant of that half angle. So let's apply this to a few examples. So example 6 says to use the half angle formula to find the exact value of these two. Let's start with part A. We're given the cosine of 15 degrees. Well, 15 is half of 30. So we can say this can be expressed as the cosine of 30 degrees divided by 2. And let's just reference our formula. For cosine of a half angle, you want to use this one. So this would be plus or minus the square root of 1 plus, now this will be the cosine of 30 degrees, divided by 2. So let's evaluate here. So should we use the plus or minus? Well, 15 degrees is in quadrant 1. So it should be positive. Cosine will be positive in the first quadrant. So this will become plus the square root of 1 plus the cosine of 30 degrees is the square root of 3 over 2. And this is over 2. So kind of a messy square root here. So let's try to get rid of this double fraction and combine things as much as possible. I can view that 1 as 2 over 2. So let me just write this out here. This is 2 over 2 plus the square root of 3 over 2 all over 2. So that would combine into 2 plus the square root of 3 over 2 itself over 2. So if we're dividing by 2, this is like 2 over 1. We can view it as a division of two fractions. That's going to flip and multiply. Basically, that 2 is going to multiply with the 2 in the denominator up top. So we can write this as the square root of 2 plus the square root of 3 over 4. And then we can take the square root of 4 in the denominator. So we can split this between the numerator and denominator. We can write this as the square root of 2 plus the square root of 3 over 2. Still have this double square root, which is a little bit strange, but we at least have the double fractions simplified. All right, let's look at part B. We have the sine of negative 15 degrees. So we can express this as the sine of negative 30 degrees over 2. We can deal with the sine of negative 30 easy enough. So let's use our formula for half angle for the sine. So this time we're using this one, plus or minus the square root of 1 minus the cosine of alpha, where alpha is what we're dividing by 2 here, over 2. So this will be plus or minus the square root of 1 minus the cosine of negative 30 degrees over 2. All right, so let's evaluate the cosine of negative 30 degrees. That would have the coordinate point, that's like negative pi over 6, so that would be positive root 3 over 2, negative 1/2. So our cosine is root 3 over 2. And since we are in the fourth quadrant, the sign should ultimately be negative, since negative 15 degrees is in quadrant 4. So let's take the negative version of this square root here. So it'll be negative square root of 1 minus root 3 over 2. These parentheses here. Over 2. So let's I'll show a different approach for simplifying this double fraction. We could multiply the top and bottom by 2. So I'm thinking about wanting to cancel that 2. Oops. Let's come back up here. So imagine distributing a 2 through to both terms in the numerator, and the denominator will also get multiplied by 2. So it will hit that 1, so 2 times 1 is 2, minus, and we'll just get the square root of 3, because this 2 will cancel with the 2 that we're multiplying. And then in the denominator we'll get 4. And then let's apply the square root to the numerator and the denominator. So we could say negative square root of 2 minus the square root of 3 just over 2, since the square root of 4 is 2. This might be a little bit more simple than that double fraction process from earlier, but we get the same result. So you can either get a common denominator here, combine them, and divide the double fractions, or just think of what you should multiply in order to cancel this denominator here. All right, we have one more example. Let's take a look. So now they tell us that the cosine of alpha is negative 3 over 5. Alpha is between pi and 3 pi over 2. So we must be in the, well, let's think about where our half angle will be as well. But let's just start with our given information. We have the cosine of alpha being negative 3/5. So let's just jump into part A, and we'll think about what we need to determine in terms of which quadrant the half angle is in. So we're looking at the sine of alpha over 2. Well, following our formula, it would be plus or minus the square root of 1 minus the cosine of alpha over 2. So we do need to determine if the sine of half of alpha, we have the cosine of alpha here, if the sine of half of alpha is positive or negative. So let's look at this inequality that they give us. So they tell us that alpha is in between pi and in between 3 pi over 2. Well, we can just divide all sides of this inequality by 2, because that will give us alpha over 2 in the middle. So this would be in between pi over 2 and 3 pi over 4. So that tells us that this half angle, alpha over 2, is in quadrant 2. So the sine in quadrant 2 should be positive. So let's take the positive version of this square root. And then we're given the value of cosine of alpha, so we can plug that in here as well. So this will be equal to positive square root of 1 minus negative 3/5. That's the cosine of alpha over 2. So let's just get rid of that double negative. This becomes the square root of 1 plus 3/5 over 2. So let's do that trick again of clearing out this denominator by multiplying by 5 on the top and bottom. Inside of the square root. So that will give me 5 plus 3 over 10, because the 5 distributes to the 1. 5 times 3/5 will cancel with the 5 in the denominator, and then 5 times 2 down there gives us the 10. So we get 8 over 10. Which if we divide each of those by 2 will give us 4 over 5. I know the square root of 4 is 2, so we have 2 over the square root of 5, and then let's just rationalize the denominator. So if we multiply by root 5 over root 5, we'll get 2 root 5 over 5. So that was for the sine of alpha over 2. So let's do a similar thing with the cosine. So first I'll write out the formula that we had. The cosine of alpha over 2 will be plus or minus the square root of 1 plus the cosine of alpha over 2. Now, should it be positive or negative? We said earlier that alpha over 2 was in quadrant 2. So the cosine should definitely be negative in quadrant 2. So let's take the negative version of this. So this will be equal to negative square root of 1 plus the cosine of alpha. We said earlier the cosine of alpha, this was given in the problem, was negative 3 over 5. Over 2. So this will be negative square root of 1 minus 3 over 5 over 2. Let's multiply the numerator and denominator by 2, or I'm sorry, by 5, so we can clear out that double fraction again. So this will give us negative square root of 5 minus 3 over 10. So again, the 5 is hitting the 1, becoming a 5. 5 times negative 3/5 will be negative 3, and then 5 times 2 is 10. So we get negative square root of 2 over 10, which is negative square root of 1 over 5. The square root of 1 is 1, so we get negative 1 over root 5, and then we can rationalize again. So that will give us negative root 5 over 5. So let's do the same thing for the tangent. I'm just looking at the example here, because we could have taken another approach as well. Since we knew what the sine of alpha over 2 was, we could have maybe built a triangle or used the Pythagorean identity to find the cosine. But it's good to use these formulas as well to practice using these. All right, let's look at the tangent, and let's use this half angle formula for the tangent given here. So plus or minus square root of 1 minus cosine alpha over 1 plus cosine alpha. So let me write that down here again. So this is part C. Yeah. Let's find the tangent of alpha over 2. I'll rewrite the formula: plus or minus square root of 1 minus cosine alpha over 1 plus cosine alpha. And just to recall, we said cosine alpha was negative 3/5. So let's plug everything in, and we are still in quadrant 2 for alpha over 2, so the tangent should be negative. So negative square root of 1 minus negative 3/5 over 1 plus 3/5. So let's get rid of that double negative. So that will be the square root of 1 plus 3/5 over 1, oh, and this should be negative here, over 1 minus 3/5. Yeah, because we're plugging in negative 3/5 for each of these cosines. So we can either turn the 1's into 5 over 5 and combine the fractions, deal with the double fraction, or we can multiply the top and the bottom by 5. I'm going to take that approach. So tangent should be negative, so I need to keep my negative in front. So this will become 5 plus 3 over 5 minus 3. So we have negative square root of 8 over 2. So negative square root of 4, which this one reduces nicely to just negative 2. So with these half angles, you may be given information about where, in this case, alpha was, but we still need to figure out where half of that angle is. We saw that this was going to be in quadrant 2. So if they give you, and let me just scroll back up to the question description, if they give you some inequality like this, we can just divide all parts of the inequality by 2 in order to find out where that half angle is. And that will inform us on what should be positive or negative. All right, so this was a pretty tricky section. There's a lot of identities that are being built into our list. We'll see a few more in our next section. So I would keep maybe like a running sheet of all of our identities. We have our base ones like our reciprocal and quotient identities. Last time we saw the double angle, or this was about the double angle and half angle identities. We also saw sum and difference identities for sine, cosine, and tangent. We also have our Pythagorean identities. So the list is growing larger and larger with each successive section that we go through. So at a certain point, there's only so much we can remember. A lot of these, you'll just want to reference the formulas. Some of them you can derive from more simple identities. Like we saw, we could get the double angle identities using angle addition and things like that. So try to develop techniques to remember as much as possible. But for now, I would want to just practice using these, plugging values in, and thinking about which quadrant we should be in. And that will be a good start. Okay, that's it for this video. So we use double angle formulas to find exact values. we used double angle formulas to establish identities, and then we used half angle formulas to find exact values. That's where we left off. That'll be it for this video, and I'll see you next time.